Okay, let's try this again here. Okay, I'm going to go ahead and get started here. As with last week, I'm kind of switching the topic a little bit and going off onto a special topic that is covered on your final exam, and I have not covered in this class, so we're having to go through and discuss it a little bit here. And that's analog to digital conversion and digital to analog conversion. If you look at this course, it's interfacing, and a lot of what we do is interfacing, and I'll talk a little bit more probably next week on doing analog to digital conversion with our particular microprocessor. As you look at our microprocessor, it does have analog to digital built into it. Of course, our microprocessor has got 20 some pins roughly, and but it has built into it up to, I think it's 9 or 8 analog, 8 or 9 of our pins can be analog inputs. And there are many applications for analog inputs. And actually, the boards that we're using have a potentiometer there for writing a lab for that there. So I've as before, I've kind of swiped these slides there. So let's kind of look at a little bit of what we're looking at here. Is the real world as we know it is analog, right? You don't feel that way anymore because you're in a generation where more and more of, as I grew up, everything was analog. Television was analog, signals that came through an antenna. Radio was analog. Music, believe it or not, was the old record player that had the music that they went around, and there was little grooves that the actual sound was actually in the grooves, and the needle would vibrate, and the vibrations were then amplified and sent out to the speakers. Now, of course, 80%, 90% of the world that you're looking at is digital. That's it. So, unfortunately, the world is still analog. The human ear does not hear digital sound. It hears analog sound. We have to transpose our sound that we record digitally back to an analog signal in order to feed our loudspeakers or our headphones or whatever we're listening to. The same thing. A singer that goes through and sings and records a new CD, and I don't know who's popular in Malaysia right now, but whoever it was, back in my day it was Black Sabbath and Ozzy Osbourne, but if anybody's ever heard of those folks, but regardless, when they go into a studio recording, if they play a guitar, they're vibrating a string in an analog fashion, right there. When they sing in an analog microphone. Those signals have to be converted into digital signals before they can be placed into, recorded. Now, back in my day, of course, they recorded things on the analog tape, and then the analog tapes would go through an analog mixer, and they would produce albums that way. Nowadays, I say nowadays as if things have changed. When they record the song, the music is recorded digitally on the spot. The analog to digital conversion is done in the studio during the recording process, and the mixing is all done there. And I don't know how many of you are familiar with the music recording process, but typically it's done in tracks. So the lead singer would go in there and sing one track. The instruments. The music recording industry is not like a concert. You go to a concert and everybody performs at one time, and all the music is done. The recording is typically done in layers, in tracks, and during that process, you record one layer, and then, it may be the piano, the piano may be recorded first, and then the person who plays the drums can come in and record on top of that. There. Or multiple instruments we play. The audio or the lead singer may record as a solo artist at the end after all the instrumentation is done. But it's done in layers. And these are done, each of these layers are recorded digitally today. Back in the old days, and when I say the old days, I'm only talking 20 years ago, but to you that's ancient history, 20 years ago. For someone like me, that's relative. That was done in the analog fashion. It used to be a big deal when an artist would sit down and record an entire album by themselves. They would play all the instruments, and they would record one track and then record the next track. Now it's not so uncommon. But we go through this process, and two things happen when we convert to binary. That's there. One thing we're going to do is we're going to, when we digitize the signal, we quantize it. When I say quantize it, it means we take it from an infinite number of levels to a finite number of levels. Right there. So if we're looking at a 12-bit A to D, which is what the 8051 has, then you've got 2 to the 12th, which is about 4,096 levels that we can record. The human ear can hear an infinite number of levels, so we've got this quantizing effect. Then the other effect we have is a sampling effect. In other words, we're taking it at discrete samples. Toward the end of today's discussion, I want to talk about something called the Nyquist theorem, and that's the process of when you record audio, how fast you have to sample. Actually, it's not just audio, any signal that's there. But we've got two processes. One is the digital to analog conversion, which is actually the simpler of the two processes, and the other is the analog to digital conversion right there. So obviously, if we want to take data and we want to sample it and put it into a computer, we have to go through an analog digital conversion. If we want to take the data out, we want to go through an analog. Now, for control systems, our requirements are much different. We may want to sample, when we look at embedded systems, we may want to sample things such as temperature. The temperature in a room is an analog quantity. It's somewhere between, if you grew up in the state of Minnesota like I did, you might see sometimes the outside temperature might hit minus 35. If you happen to be in Malaysia, sometimes in June or July, the temperature might be plus 35, right? That's there. So we've got this range of temperatures. That's there. So we may want to sample temperature. That's one thing. Another thing we may want to sample is velocity. Now, velocity can be sampled digitally or it can be sampled by analog methods. But temperature is a good example of stuff we may want to sample for a control application. We may want to sample the fluid level in a tank that uses a resistive float right there. So we have many applications where we want to do analog to digital conversion. In the control world, we don't do a lot of analog or digital to analog. And the reason is that typically we're going to turn on things such as heaters and motors and servos. We're not going to feed them analog signals. We're going to feed them digital signals that are used something called pulse width modulation, where we vary the pulse width, which again is another form of analog to digital or digital to analog conversion. But we have to convert some of our signals because what we want to do, for example, in a control system, we monitor the speed of a vehicle. If it's too fast, we want to slow the motor down. If it's too slow, we want to speed the motor up. So we have to monitor the speed. That's there. But that is quite often. If we want to monitor the temperature in a room, we monitor the temperature. If it's above 26 degrees, we turn on the air conditioning. Turning on the air conditioning is a digital signal. It's on or off. The temperature gets below 23, we turn the air conditioner back off. Right there. So that's typically a digital. So we don't do as much digital to analog, but we do a lot more analog to digital. And if you look at our 8051, it's equipped for a lot more of that there. So digital to analog, we'll talk about basically right there. Here we've got a Computer, it feeds into an A to D, and this is A to D, it should be a D to A converter. Up there. That's what I get for being lazy and not typing my own slides. Up there. There. And this happens to be 8 bits. Now when we look at this right here, what we're going to see out of this is we get, right here, as we look at this right here, this is 8 bits. We've got 256 levels that we can have here. Now we can either go minus 5 volts to plus 5 volts. We could go minus 1 volt to plus 1 volt. We could go 0 volts to 5 volts. We can set this up to whatever range we have, but we have, with 8 bits, we have 256 levels. That's what we have. Our lowest level, which I'm going to assume is somewhere right around here, is going to be 0, 0, 0, 0, 8 zeros. Our highest level we can represent is FF, right there. And we have a digital signal in between each one of those right there. So typically it's 5 volts. This slide is a little dated. Our processor typically is using a 3 volt reference or a 3.3 volt reference right there. We could set up our reference voltage on our A to D to whatever we want. And as we get into more of the detail of our 8051, we'll see that there's a pin that we select our input, or we can tell it to use VCC as our reference. But whenever we do analog to digital or digital to analog, we have to select a V reference. And V reference is going to represent our maximum value right there. And we're going to, for sake of our discussion, we're only going to go to 0, but we can go to negative. So we can have a plus V reference and a minus V reference. I'm going to treat our minus V reference as ground right there. So we have our references right there. So a simple D to A converter is a very simple summing amplifier. Does everyone know what I mean by a summing amplifier? Have you had, in your analog courses, have you had op amps? Right there. I don't know if these slides go through that there. Right here. But this is a simple summing amplifier. Let me just kind of, right here, there, let me grab my pen. And typically what you have here, and let me bring up my OneNote right here. There. And I'm not going to spend a great deal of time on this subject because it's not going to be on the final, but it does help in understanding. And where is our OneNote? This is still converting. Right. Oh, it's almost done. That's there. No wonder my processor is slow. Open OneNote. Why is what other? There we go. If we take an op amp, an op amp looks like this right here, and I'm going to show it plus minus in this direction right here. And I'm going to ground this right here, and minus V. These are our power controls for our op amp. And have you seen op amps before? Please say yes. If not, that there, I'm going to be good at there. But an op amp is an amplifier that amplifies the difference between these two voltages right here. Right here. And if we take a, right here, this is an inverting amplifier in an op amp circuit right here. It amplifies the difference between the two of these voltages there. And what we end up here, this is, and right there. What we've got here is, let's just call this RI, and this is RF. And what we have here is we have a voltage coming into this here, VN. And we assume that this to be 0 volts. We have a current going in here, and this current goes back here. And our output, V out, is equal to RF over RI times Vn, and it's negative. It's an inverting amplifier right there. So this is an inverting amplifier right there. And if you haven't seen this in your electronics courses, you will see this in your electronics courses. Now, as it turns out, we can have two of these right here. Right here. Right here. Right here. I'm going to call this RF. I'm going to call this V1, V2, and I'm going to call this R1, R2 right there. Right there. And V out, in this particular case, V out is going to be equal to, right here, and I'm going to call it V1 divided by R1 plus V2 divided by R2 times RF, put a minus in here, right there. So in other words, what we are doing is we can sum the two voltages up together, right there. We can add the two. This is called a summing amplifier, right there. So, and we can put a weight on each one of these voltages that we choose, right there. And then we have a master gain that we can control the gain right there. So this is called a summing amplifier. And by using a summing amplifier, right there, going back to, and I want to leave that right there. Let me close this right here. Close this right here. Let me go back to my circuit right here. Is that by using a summing amplifier right here, by putting an amplifier here, right here, that's what I mean, that we could set this up to where we could weigh each one of these inputs directly. So this particular one here, this is C0 divided by R plus D1 divided by 2R, so I'm putting up a 2R plus 4D1 R plus 8D2R. So what you're seeing here is that I can weigh each one of these here, where D3 is worth 8 times the value of D1, right there. So I can set up this 4-bit digital analog converter right there. So it's very easy to convert things from the digital world to analog, as we could set up these summing amplifiers. Now, as it turns out, that this is a little bit messy, and we typically would do this on an IC because these resistors have to be fairly accurate. That there, and requires a wide range, a 10-bit. It's going to require resistors that go from R to R divided by 1024. That there, usually you would use this is just some calculations right there. The one thing I should point out is this number right here is one of the things you want to look at here, is that the smallest step voltage, V step, is going to be equal to V reference right there divided by 2 to the n. This is a formula that you need to know right there. You need to know this formula right there. And I should say that you need to know that so importantly that you will probably have to make sure you know it before you take your final exam, because there'll probably be at least one question where you'll be asked, what is the step voltage for a 12-bit A to D with V reference? That's there. So, for example, for a problem is V reference might be 3 volts right there, and N is 12. What is our step voltage right there? and you just plug those numbers in right there. So, and you may be asked another question that would say you need a resolution of exactly how many, and this is also often referred to as the voltage resolution. How accurately can we represent that there? 12 bits is actually pretty accurate, because that's 3 volts divided by 4,096 right there. So, okay. Right there. So there's another way of doing this up there that's a little easier, and that is that we still stick in R and 2R. We only need 2 values of resistors. I'm not going to go through this circuit. It's not that important for this class, because typically if we're going to do A to D or D to A's, we would just buy a D to A off the shelf up there. But this is how they work right there. So again, this is how what we're looking at here, and this is showing a voltage here. This is actually set up as a electronic workbench simulation that there. Normally, again, what we're doing is we're taking this and we're amplifying that voltage through an amplifier right there. Right there. So again, we're looking at, this is the level of each of the bits right there. And again, we're saying that our most significant bit is half of V reference, fourth of V reference, eighth of V reference, and 16th of V reference. That's what we would expect to see on a 4-bit A to D. That's the weighting of each one of those. So all this is saying is if we were to look at this particular circuit and analyze it, it would give us the results of what we would expect for a 4-bit digital to analog converter. Because again, if we're looking at, if V reference is equal to 5 volts right there, this value right here is the number 8 right there. So this is the number 8000. 8 is roughly half of 5 volts. So that would represent the number 2.5 volts right there. So another thing you need to know, as we're looking at this right here, is that the actual voltage measured is going to be equal to the binary number we measure. I'm going to call it reading, max reading, times V reference right there. Is what we're essentially say right there. So 8 divided by 15 is actually going to be a little bit more than 2.5 volts right there. But it's close enough. It's going to be roughly half right there. So we're looking at this right here. This is going through the same type of calculation right there. I just simplified it to this little formula right there. Right there. So if we look at this right here, if I take the number 1011 over 1111 times 5 volts, it should be roughly 3.4 volts right there. That's what we're looking at right there. So, got there, and I'm going to skip through that there. Analog to digital is more what I'm concerned about right there, and that's taking an analog signal and we're converting to digital right there, and we're going through the same process right there. This is 8 bits. The ideal takes a linear analog, converts it perfectly to a digital. Now the way that these work are somewhat interesting, but we'll talk a little bit about that later right there. So here we're looking at 0 volts is going to be 000, 5 volts is 1111. It's actually going to be a little bit different than that there, but that's close enough for what we're looking at right there. So an 8-bit converter will represent within 1 part 256. That's there. Again, you do have an inherency of about half a least significant bit. It depends on your A to D converter. Some A to D converters will work this way. Here's your analog signal. And some will look like this right here, which means our maximum error is one of the least significant bit. Others will operate this way, where our maximum error is roughly half right there. So you can see there's two different ways. See, this triggers right here at half the least significant bit. This waits till it gets to that value before it triggers. Different A to Ds work differently at there. So an A bit can represent within one part or about their inherent uncertainty of plus or minus half a least significant bit. I'm going to say that some of them will give you an error up to one least significant bit. In this particular case, we're looking at 5 volts divided by 256 gives our maximum error right there. That's the distance between each measurement right there. So again, it goes through the same calculation right there. So again, this is the same slot that I showed one least right there. This is our conversion factor that we're looking at right there. So this is our number of bits there. This is the table for 5 volts. Remember that our microprocessor uses 3 or 3 point right there. Any question you would see on the final exam, this value would be given to you. Right there. So again, this is the resolution. This is the number of bits, and this value right here is equal to, in this particular case, 5 volts divided by 2 to the 6 right there. And I can right there. Put my calculator. So 5 divided by 2 raised to the 6th equals 0.78 right there. And slideshow from current slide right there. See, and that's where that 78.1 milliamps comes from. So that's the formula that you need to know, is that your increment is equal to V reference, and I'm repeating this at there, divided by 2 to the n, where n is the number of bits. Bits for your A to D converter right there. So you'll hear the term, 12-bit, 10-bit, 16-bit A to D right there. Now, this also will come back to another term which we won't talk about much, is signal-to-noise ratio. That's there. Because your maximum noise is at there. Your signal-noise ratio is 20 times the amount of noise divided by your max signal right there. And if you want a particular signal-noise ratio, you have to increase the resolution right there. As it turns out, the human ear is incapable of hearing a signal-to-noise ratio noise if it's greater than 100 decibels, 100 dB signal-noise ratio. Types to A to D converters. I'm going to go through this very quickly. You don't need to know this. I'm just going through the slide right there. Really, the only thing you need to know from the discussion today is the resolution calculation right there. So, intergating type or dual slope, parallel or flash, etc. right there. This is the most common one right there. Is right there. And this is the only one I'm going to spend any time on, is this is a counter type. As I mentioned before, coming up with a digital to analog converter is very easy, right? So what we do is we have a counter right here that's just going to count from 0 to 2 to the n. So it's going to count from 0 to 4096, and it's going to feed the output of the counter into a digital to analog converter right there. That's going to go into our comparator. As soon as that comparator trips, in other words, Vn is greater than or equal to VDAC, the output of the digital analog converter, that's going to trip. And then that's going to say that output then becomes our analog signal or digital signal. right there. So if this is, we're going to say, for example, this is B reference. B reference is equal to 3 volts right there. And this is, input here is 1.25 volts. Somewhere right around, you know, if this is a, we'll just say an 8-bit, somewhere right around the, you know, the number 110 or so, this is going to trigger, and we're going to output the 110. So, and we just keep repeating this process. We start the clock. This counter counts from 0 up. As soon as the comparator trips, that's our digital output. It's a very easy process right there. Only problem is that it takes time. Right there. It's going to take a little bit of time. This again is the most common one used. And the reason is it's very simple. Counters, as we talked about, are very easy to come up with. You know, 4 flip-flops or 8 flip-flops, we have an 8-bit counter, right? 8 flip-flops connected up. We have some control logic that we write a 1 to a particular bit in our register. That tells our counter to start counting. And then when this thing trips, it's going to flag an interrupt and say that it's done converting. Go read the data. So this is the type that we're going to be looking at right there. It's a very simple counter type right there. And again, what it relies on the fact is that there's an internal digital to analog converter right there. So that's the most common right there. So our control logic is received. Control logic initializes, sets the counter to 0. Turns on the clock, sending regular pulses to the counter. Right there, the counter keeps clocking up there. So this just tells the clock right there. As the clock center outputs a digital signal to the analog digital converter. Right there. Of course, I stole some really pretty slides this time. Right there. And then when this output generates a staircase. Right there. So we're going to see there's our staircase going to our converter right there. So you can see as our count goes up, our voltage goes up right there in a nice staircase. At some point, it's going to cross right there, and it turns off the clock right there. So as soon as we hit this point here, this crosses right here. That converter, that comparator, all it does is compare the output of the digital analog converter to the input signal that we want to measure. And as soon as that triggers, right there, it's done. So this is the time it took to convert right there. Now, the specified conversion time is the time it would take to read the max of the signal. So our conversion time varies with this type of A to D. And the reason it varies is the sooner the comparator trips, which is the lower the voltage, the sooner that there. Depends on the input signal size. Once it's been read, we start the process over again. Varying rapidly, count, reset. Now there are other types, tracking, that it uses an up and down counter that will keep track of where it was at the last time and count down or count up depending on what direction it thinks it's going to go. So we don't start at 0, we start where we at last time, and we'll count down. If we realize we're going the wrong direction, we start counting up right there. So we can use that with a tracking A to D. It's a little bit faster, it requires a little bit more logic in that there. This one here uses an integrator right there. This one's a little bit different in the fact that it doesn't have a direct counter that feeds to an A to D. What it has is it has a signal that goes up like this, and we know the slope of this signal right there. So we start this thing going up, and we measure the time before it trips. And that time represents it's very similar to what we had with the counter, except for we don't have the D to A. We just have this integrator, which simply has a voltage that rises at a known rate. The problem with this is that this relies very heavily on a very accurate integration process right there. But it saves a little bit, takes up a little bit less space, a little bit simpler. That's the dual slope right there. Again, conversion is applied, the op-amp integrator, and right there is applied to the comparator, and then when it trips, the output of the clock, right there, overflow is sent there, activates right there. So it works a little bit different right there. So I'm not going to go through that in great detail. It goes through that there. Flash converters, that they're extremely fast. They're very costly. Here, what we're doing is it's just basically we have multiple comparators for what we're doing right there. Right there. And we apply a different analog voltage to each comparator right there. And we look at the input and we see which comparator is active right there. So we compare it to multiple voltages at the same time. This is very fast, very expensive right there. And I'm going to kind of wrap that discussion up. I don't think there's anything else I need. Excess approximations, that there again, we try to guess and we go up and down. It's kind of like a binary search if you do searches right there. See? So it goes through. So we look at the first one, we decide is it higher or lower, and then we go to the next one. So it's like and I don't think you had binary searches, but if you want to find a value, you look at the middle. All right, is it in the first half or the bottom half? All right, it's in the bottom half, so we look in the middle here. Is it here? And we get closer each time. Again, a little bit more logic to it right there. A lot of the commercial ones will go through this way right there. Okay, that's all I have on this one here. I have a couple other topics I just want to mention right here, and I want to just kind of mention this right here. Is there's something called the Nyquist theorem. And this is a subject that's well beyond, in great detail, where we're at in this course, or any of your courses. But the Nyquist theorem basically says that if I take an analog signal that is band limited, this is a key word, band limited means that it's been low pass filtered where there's no frequency above a certain frequency in that signal. Now, typically, when we're talking about band signals, we're not sampling a single sine wave. We're sampling something like somebody's voice, or a musical instrument, or we're sampling noise of some type that's there. Now, in control theory, we don't necessarily worry about noise in terms of we're measuring a temperature that's there. We don't carry, we're only measuring a snapshot that's there. But if we're doing sampling where we want to reproduce our signal back, and that's usually if we're talking audio signals or video signals or something like that, or we want to reproduce the signal. So we want to store it on a CD, or in today's world, an MP3 file, they're digitally, and we want to play it back, and we want it to sound like the original. So that if it's been sampled at least twice the highest frequency contained, then you will be able to reconstruct that signal exactly the same right there. Now, what that basically means is that the human ear is supposed to, at the age of 20 roughly, or 16, 17, before you start damaging your ears with old age, will hear a range between about 20 hertz and 20 kilohertz. That's the range of the human ear. As you get older, as I said, when I was younger, I listened to rock bands like Black Sabbath and things like that, and we listened to them very loud. that there. You damage your ears as you get older. The natural aging process means that the hair follicles within your ear get a little stiffer and they're not quite as responsive to higher frequencies, so that goes down a little bit. So I doubt if my ears can hear 20 kilohertz anymore. But regardless, we're going to use 20 kilohertz as the reference point for the maximum audio sound that the human ear is able to respond to. That's there. So that means if I want to record any type of audio and play it back at the highest resolution that you can hear, and see that's a key thing that you can hear, then I can bandpass limit that to 20 kilohertz. So 20 kilohertz is the highest frequency that I want to record. Now before I do that, I have to low pass filter it to 20 kilohertz. And I'll get into why I have to filter that out, because I just said that you can't hear anything above 20 kilohertz. Who cares if it's there? But something very unique happens when you digitize the signal. That's there. And it's called aliasing. We'll talk about what aliasing is here in a second there. So we have to make sure that anything beyond 20 kilohertz is gone. That's there. And that's easy to do. We stick in a a high resolution low pass filter and it chops it off. That's there. So CD quality sound, what you listen to when you listen to your MP3 players or your iPhones or whatever, it's typically what they call CD quality sound. And CD quality sound is recorded at 44 kilohertz is the sampling rate. It's a little bit higher than the 40 kilohertz that's required in order to give it some room for that filter to roll off right there. So we bandpass filter it down to 20 kilohertz. We give it about an extra 2 kilohertz for the filter to roll off. That's there. And so we listen to anything that's there is going to be played back. That's there. So if F is the largest frequency, you must sample more than 10 times to look like the original when plotted. Now this second one doesn't really apply. It's the first one that is the one that we're looking at is the Nyquist theorem, because that's the one, because what we're going to do is we're going to be looking at the signal when we low pass filter it again on the other end, right there. And what happens here is this is a signal sampled at 200 hertz, sampled at 2000 hertz. This is going through his discussion where he says that, in order for it to look like it, you have to sample it like 10 times. We don't care whether it looks like it or not, because if we run it through a low pass filter, it's going to look like it anyway, right there. So it doesn't really matter. But that's there. But what we're sampling is these are our points that we sample right here. Now, this is what happens if you sample at exactly half, or at the same, at twice the frequency right here. This is right there. This is 1,000 hertz sampled at 2 kilohertz. You notice that what do we get there? You got a nice DC level right there. So in other words, you don't get anything. So as soon as you sample at twice, this is 1,000 hertz signal sampled at there. So you have to sample it more often than that, right there. So you've got 1,000 hertz sampled at 2 kilohertz, and you've lost all the information. It's not there anymore. So here we've got a 22 right there. And see, what we're looking at right here, and this is kind of a strange thing, is it looks like this data right here. The actual data is 2200 hertz, but it looks like it's only about 200 hertz right there. So we get this aliasing effect right there. So we get at there, and this is what, I'm just going to disregard this right here and just go to one note. It's easier for me to do the one note than it is for me to try to use this slide. But what we find is that if we sample a signal right here, and if we sample it, say, at twice the frequency, and we get it here and here, or we get it here and here, right there, we can get that data back, right there. So you know, if we can get that back. Now, what we find is if we take this signal and we sample between, this is the frequency, and this is our frequency out, right there, between there and the Nyquist frequency. It looks like this, but then it starts folding back over, and then it repeats right here. So if we sample at the exact same frequency, we get DC out there. So what we're going to find here is that this is 20 kHz right here. If we've got data here that say at 30 kHz, that's going to show up as a 10 kilohertz signal. So even though you can't hear it before you record it, once you recorded this signal that's sitting there at 30 kilohertz, now all of a sudden is within the range of the human ear. It's folded back. So as a result, we have to make sure that we low pass filter through this right there. And the only reason I'm going through this discussion at there is I want to get across that normally, whenever we're going to take an analog signal right here, here's our analog signal, and we're going to sample it, our first stage is going to be a low-pass filter. This is called an anti-aliasing filter. Filter right there. We have to filter that before we sample it, right there. If we don't filter it, and then we go through our analog to digital conversion process. If we don't filter it, things that are in this signal before we sampled it that we didn't care about, we couldn't even see it, it didn't measure it, can show up over here because of aliasing. We're introducing a new type of noise that didn't exist because we're taking a signal, say that, again, we'll look at our analog. We've got some noise at 30 kilohertz right here, right there. We've got some noise which our ear couldn't hear. Now, if we had a dog, the dog might bark at it. That there, because dogs have a range beyond that of the human ear. I don't know what the range of a dog is. It may not be 30 kilohertz. So, you know, if you had a pet bat, it might hear it, right there. But as a human, we can't hear that 30. That there. But once we sample that, and we're sampling this at 44 kilohertz, right there. That's our sampling rate. Now all of a sudden, this now is going to look at something like 14 kilohertz, right there. So now all of a sudden, this now looks like 14 kilohertz noise. And we can hear it. It's now there. That's there. So it's very important that we get rid of that. Right there. So, you know, a couple of other comments on this whole discussion about sampling that's there is when we look at sampling rates, I mentioned CD quality being it's sampled at 44 kilohertz. So it's typically band pass limited at 20 kHz right there is our band pass that we're looking at right there. And that gets you pretty much the maximum quality that anybody cares about right there. Now, there are some things that are done with MP3 files. This is not a course on digital signal processing where you get a little bit less. There's some losses when you convert, if you store music as a FLAC file, it's considered a lossless algorithm. If you report it as MP3, there's some losses that some people can hear, other people say that you can't hear it. As I can guarantee at my age of 58, I don't hear the difference between MP3 and CD. At 22 or 19 or how old some of you are, you might be able to hear the difference. But at 58, I don't hear the difference anymore, right there. So I'm just pointing that out. But if you look at, say, for example, telephone quality, that's a sampling rate of 8 kilohertz. Its bandpass limited to 3 kilohertz, right there. Now, have you ever talked to anybody on the phone that, that you're familiar with their voice, but they don't sound the same on the phone? And that's because at 3 kilohertz, you can understand the conversation and you can tell the difference between most people, right there. But you don't necessarily, you lose a lot of that higher frequency information that's not important for a phone conversation. Right there. When I record with this little headset audio, I'm not recording at CD quality sound. I'm probably bandpass limited, probably down to 5 or 6 kilohertz. That there. But you don't care, I'm not, I'm not some rock star that you care about the quality of my voice. You're only caring about what I said. I always like to use the example of my ex-wife and her sister. That there. I had an ex-wife that liked to call me quite frequently and ask silly questions like, "Where are you? How long are you going to be there?" I mean, she'd call 10 times an hour. That's there. So, and I was driving. I dropped off her mother at her sister's house, and her sister was at work. So I dropped her off on my way to work. That's there. I get a phone call. "Where are you?" I'm pulling off the highway. Almost to work. "Did you drop Mom off?" "Yes." "Okay." And hung up. End of conversation. As I said, this ex-wife had very short conversation. 40 seconds later, my phone rings again. Exact same question. "Where are you?" "I'm getting off the highway. I'm ready to work." "Did you drop Mom off?" "Yes." "Yes." And then all of a sudden I thought, "Who are you?" And what I didn't realize is that my sister-in-law called me first. That's there. The two of them, who I can tell the two of them apart very easily sitting in the same room. They don't look the same. They don't necessarily sound the same. But they had very similar patterns with the way that they held conversation. They were both very abrupt and rude type people. One of the reasons she's an ex, that's there. But regardless, on the phone, I could not tell the difference between the two of them. That's there. Very much that there. And that's because I can recognize, somebody's voice that's band limited at 20 kilohertz. I can tell, about the only English singer I know, say, City Nora Lisa from somebody else. Very unique voice, I can tell that. But as soon as you play that same song over a telephone where it's band limited 3 kilohertz, all of a sudden that upper information that makes that voice unique is gone. But the important thing is the conversation, what is said, is still maintained right there. So as we look at sampling signals that there, sometimes we band limit that there, we don't lose information that's important, sometimes we do. That there. If we're doing a control system, if we're trying to maintain the temperature of a room, sampling once every 3 minutes might be more than adequate. Right there. But if we're trying to maintain the speed of a jet engine, sampling every 3 minutes could be disastrous. So our sampling rate is quite often a function of what we're trying to do. Right there. In control applications, it's different than trying to reproduce audio. And even in audio, the sampling rate is that there. But going back to our aliasing, we have to maintain the fact that that extra information, if it's folded back, it's going to create noise. If I take my audio signal that's fed into my telephone and I don't band limit to 3 kilohertz, it's totally inaudible. You can't hear anything because you've got so much information above that 4 kilohertz aliasing filter that you can't understand it. It's just garbage. So you have to sample it down to 3 kilohertz. Audio signals for CDs, for example, you don't hear noise, harmonics, say, on a piano that are above 20 kilohertz, but they exist. They're there. And if you don't band limit there, you're going to hear them, and it's going to create noise, and it's not going to be a very good quality noise that you're going to enjoy out there. So that anti-aliasing filter is very, very important. So tomorrow I will be talking about I think tomorrow I'm going to be assigning the final dishwasher assignment out there. I'm going to be putting that out there. So I'll be talking about that here in the lab tomorrow in Thursday's group. Now, how many people in the Thursday group are planning on sneaking out early? Nobody's going to admit to that. I'm going to say if you do sneak out, and the Thursday's group is small anyway, if you do, watch the recording for tomorrow, okay? Right there. I'll even be kind enough to say that I'll forget to take attendance on Thursday. So if you decide to do that, I'm not going to but I'm going to be recording tomorrow's lecture, so watch that there. I realize that Friday's a holiday, Monday's a holiday. Some of you live, what's the farthest you can live? JB is pretty far. Is Kootabaroo farther than JB from here? It's about the same distance. What's that? Which is farther? JB is farther? Get there. So I've been to both places, but I don't know the distance between the two of them. And I was just telling the instructor before this that typically my lectures are right at an hour, and here we are right at an hour. Right there.